Yeah,
All
but
right, let's
Tim,
go live.
things I do.
Things we do. All right. Good afternoon and hello, everyone. Welcome to our brand new episode of Quadcast. I am your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. We're back after our 2 week break, better than ever. So if you're watching this on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, ask us questions on the chat, and we'll get to them during the episode. And if you haven't already, do join our Discord channel so you can ask us questions there. We can answer your burning physics questions. Without further ado, let's get to it. So we've been on this theme of describing different different special particles, for lack of better words, in particle physics, from inflaton to graviton. And then last time we described the strong force mediated by gluons and talked all about that kind of like thing that confines quarks together within like a proton, neutron, etc., etc. And so, in keeping in this theme, we wanted to go to other fundamental forces. So we wanted to spend this episode talking about the weak force. And so, I guess like I want to start off by asking Tim, what is the weak force? Like, why is it even there? Because I understand electromagnetism, particles repelling each other, attracting each other. I understand from our previous discussion about the strong force, what keeps protons together. If there wasn't strong force, then everything would like repel all the protons, packed into like a nucleus, repel from each other. So there's something confining them. But weak force, like, it's not very obvious. Like, what is it and why is it needed?
Yeah, I guess embedded in that question, we have to address two different things, right? So so first of all, we're talking about forces, and as far as we know, there are four fundamental forces, and one is the strong, one's the weak force, one's the electromagnetism, and one is the gravity. Um, and I mean, you can ask the question. I mean, that's two different ways to answer this question. You can ask the question why four, right? Uh, but that to some extent it's hard to answer because these are the four that we have discovered. There could be more forces that we have not discovered yet, but four is the number that we see so far, right? So part of that is just, the answer is just that, well, there are just four forces. Now, of course, we can take another lens to this question and say, well, why the weak force? Um, and the thing is, we see four forces. Then we can flip this question around and be like, what is like embedded within that question is more like, well, what is the weak force doing, right? Um, and a lot of popular articles in Wikipedia, when you Google it, when you see the weak force, it will tell you that it is the force that's responsible for radioactive decay. So then, if you follow that train of thought, then it will mean that the reason we have the weak force is because we have radioactive decay, right? But is it just radioactive decay because we see it, there's a weak force, or is there something more? But it turns out that there is something more. It's not just simply that, you know,
Way
uh,
more.
yeah, way more. Like radioactive decay is just one facet of this weak force, and it turns out the weak force is responsible for way more things than meets the eye. So
M- Mikey, you look like you have additional things to add in that Tim's explanation just covered the tip of the iceberg. What's underneath
No.
this iceberg?
It just irked my like whenever I watch like these PBS documentaries or Neil deGrasse Tyson or something like they always say the same thing. It's like there's four forces. It's gravity, um, electromagnetism, and the strong and the weak forces. And they always say that like like Tim said, you can kind of like intuit like what a force means. Gravity, things pull together. Electromagnetism, things can attract or repel. Like these are forces, right? But then you get and then like the strong force is a little bit more confusing. But as we discussed last time, and you as you said, it's the thing that keeps nucleuses glued together. And we talked about why we don't see its effect, in everyday life, because it's very gluey. But the weak force is always a head scratcher, right? It's like, what is that? What does that even do? And everyone's always like, oh, it's responsible for radioactive decay. It's like, oh, okay, that's weird. That's it. That's it. And I think that's like a very narrow, short-sighted viewpoint of like what the weak force really is. So yeah, it's just annoying to hear people describe it as like the thing that's responsible for radioactive decay when there's like a much bigger story about it. Yeah.
Yeah, I will also add that this feeling of this kind of notion of what a force is, I don't know, maybe it's driven by like TV shows like Star Wars, whatever. Like you can feel the force. It's just like this feeling of pulling and tugging, right? But in particle physics, a force can do a lot more things, right? It's not just things attracting to each other and things repelling each other. A force really is the thing that drives change. Anytime there's a change, some kind of force is involved. And the weak force has this particular ability to actually change the type of particles that a particle is, right? So that's what makes it a little bit unfamiliar. But at the end of the day, it is a force, and it's not just radioactive decay. It's just a force that kind of involves a little bit more than just tugging and pulling.
Hmm. So actually, I want to ask a question about that because okay, like that's interesting that this can change the identity of particles. But for instance, like if you go back to like Newtonian mechanics, you have like F equals ma, and if I push on something that's a certain mass with a certain acceleration, I'm applying a force to it. So can you kind of walk us, maybe Mikey or Tim, whoever knows best, like walk us through like how did you go from that definition to this particle physics definition of like, oh, it's like a driver of change, for instance. Can you help the audience like, conceptualize around that?
Yeah, maybe I can take a step, right? Like sometimes when we push an object,
Mhm.
the only change we see is that it moved, and that's how we describe it. But in quantum physics, when something is moved, the state of something has changed,
Mhm.
right? And if you think that, well, the state of an object involves its location, I don't know how heavy it is, or some other properties, then it's very natural to say that, hey, the type of object it is, the type of particle that it is also a property, right? So in some sense, when in our everyday life, it seems like when I push my hand, the content of my hand is not changing. That may just be because of the nature of the interaction, but not actually the interaction itself. So if you look at quantum physics, you generalize a little bit, then it's very natural to say, hey, um, when I push something, the state of that something changes. It's a force. Then when the state of that something, the identity of the constituent changes, it's also a change of state. Then the only proper way to describe it, it must be also some kind of force. I mean, I don't think there's any other language really in particle physics
Mhm.
that describe that change, right? I think.
Yeah. That makes sense. I guess then, like, what's the big deal about letting particles change into other particles? Like, why is that important? Would be my
It's
question.
to add to what Tim said a little bit, like, and it kind of like I think leads into what you're asking right now is that like like from Isaac Newton to James Clerk Maxwell, like everyone had the same idea of a force. The idea that it's something that attracts or something that repels, something in
Hmm.
physical space. The discovery of the weak force, you could say that it taught us the fact that forces can be more than just that. And when you combine that with Einstein's theory of special relativity, you realize that in the absence of any forces, everything is just moving at a constant velocity, right?
Hmm.
So in a sense, there is no change going on if everything is moving at a constant velocity, right? Because all inertial, it's just an inertial reference frame. There's no change. There's no change in, there's no acceleration. So there's no dynamics. And if you, yeah, like if you combine that with this idea of like a force is anything that causes change, that's actually a much more generalized definition of what a force is. And you realize that changing the ability to like apply a force through space and time is just one type of change, but there's many other ways you can change it. Anything that causes any kind of change is called a force.
Mm.
So we've redefined our definition of what a force is, in large part thanks to the discovery of the weak force.
Gotcha. And so you can also describe it more generally, as Tim was saying, like a change in state rather than just like narrowly as just a change in like position, like when you learn from like Newtonian mechanics that if you like accelerate something, you're moving it through space. And so it's like state in space changes, but in quantum mechanics, assume it's like more general. Is that fair to say?
Yeah,
Yeah.
actually, there's also another way to think about it. You can
Uh-huh.
think of this change as in change in some abstract space. Like
Mhm.
and generally there's a term in physics we call that flavor. It's a change in the space of flavor, and that's why it's kind of like a spice in the model of particle physics. You add some spice to it, and the flavor could change a little bit, right?
Hmm. That is an interesting analogy with cooking. I guess can we take this analogy further and like maybe describe kind of like the other forces like gravity, electromagnetism, strong and weak in terms of this cooking analogy, just to kind of like layer it
Yeah.
and describe what it is.
So actually, we were talking about this last time with the gluon, right?
Yeah.
The gluon actually also changes the state of a particle. It changes. It can like when we think of a color charge, we think of three color charges. Like a quark can be either red, blue, or green. Well, a gluon is actually a process by which a quark can change its color from one to another. So in some
And
ways, it is kind of like the weak force, except we just don't notice the change in colors because
Mhm.
it's irrelevant to anything that we experience.
and just to reiterate our point from the last episode, color is not referring to the actual like color, it's
Yeah.
just a property that we give to the
Yeah.
particle, right?
Yeah.
Mhm.
It's just a name because there are three types of this such an abstract property. So that's why people
Mm.
use color as an analogy. So Mikey is right that so the quark of the color can change. So in some sense, that's kind of like a change in flavor, but then it's kind of like an undetectable one because like you would not be able to tell if a quark was at red color versus green color versus blue color
Mhm.
because you can argue that because there's a symmetry that says that they all taste the same, basically. Like a quark inside a proton that's red, green, or blue, you wouldn't notice the difference. It's still a good old proton, right?
Mhm.
But the weak force is a little different, right? The flavor we're
Mhm.
talking about are noticeable flavor. These are the and flavor. So, for example, in the weak force, electron and the neutrino, which is a different type of particle than electrons, they have very different properties are
Mhm.
considered to be in the same group but with different flavors. So these flavors are noticeable as in contrast to the color inside a quark. So that's what makes the weak force a little bit more special. That it kind of is able to drive a change in the taste. Let's put it that way.
I guess okay, so I guess like maybe I want to kind of take a step back because now we're mentioning color, flavor. That might be too many things thrown around. Can you actually give us like a real life example of like what's like a decay or interaction where the weak force appears that's like very prominent? Like if it didn't happen, life wouldn't exist.
Oh,
I'll
I
throw this
think
question to Tim.
I think the greatest one, wait, Mike, correct me if I'm wrong. It must be the neutron and the proton, right? But the neutron and the proton are very similar particle. But I'm sure anyone who has taken high school physics will know that the neutron is not the proton, right? But with the power of the weak force, the spiciest force that there is, a neutron could change its flavor. It can change into a proton by emitting, I think, an anti-electron and an electron neutrino. But let's not get into detail. It's almost like the character, I don't know, the taste of that particle is like kind of broken up, and then
Mhm.
one got like ultimately what happens is that an up quark, sorry, is it a let me think. Is it an up quark turn into? It's a down turn into an up, right? Um, yeah, a
We
neutron to
can
a
just
proton.
assume that.
Yeah,
We can
yeah,
just assume,
yeah,
yeah.
yeah. So basically, what happens is a down quark change the flavor into an up quark, right? So
Mhm.
this is a concrete process. Like the type of particle itself changed.
Mm. I guess what's the big deal about like neutrons decaying? Like just let them stay the way they are. Who cares? What would happen?
I would say that if neutrons and protons are completely indistinguishable,
Hmm.
which they are not, by the way, but without a
Yeah.
weak force, I think they would be basically indistinguishable, right? And then all this interesting uh, periodic table will almost basically disappear. Basically, you just have a mishmash. The universe will just have a mishmash of combinations of some number of protons, some number of neutrons, and in
Hmm.
some sense it would just be too much of a mess, almost like, right? Like you see some atoms here with, I don't know, 5 protons, 2 neutrons, but they are highly unlikely to be consistent. Like in real life, you know that like in the air we have a lot of nitrogen, right? But can you imagine if nitrogen, it has a highly unpredictable number of protons and neutrons? That would just be kind of a mess, basically. So kind of the weak interaction
Hmm.
helps kind of weed out all these weird combos. Like if you have too many neutrons, some of them are gonna decay away, so that you kind of have the right number of like a fixed particular number of neutrons and protons in an atom. So
Wait, hold on. I thought like the atom, the type of atom like gold, hydrogen, helium was determined by number of protons. So like if you change the number of protons, wouldn't you change like what kind of atom it is? And then also second question
mhm.
is protons and neutrons, even if the weak force weren't there, have a different charge. So they're not indistinguishable from electromagnetic point of view. So like can you clarify a little bit more what you mean like indistinguishable and like what do you mean variable number of like protons and neutrons? Like the
Okay,
protons just stay
let's
fixed.
back up here. So I think what's like so if you look at like the structure of atoms, right? Like you see that the up and the down quark, they're very similar to each other. They have a very similar mass, but it's just slightly different. Um, and then if you look at a proton, you see it has 2 up quarks and 1 down quark. Um, and if you look at a neutron, you see it has 2 down quarks and 1 up quark. And so these small differences in the up and the down quarks leads to small differences in the mass of the proton and the neutron. And that's
Mhm.
very fortunate for us because um, if the neutron happened to be heavier than the proton, then there would be this issue where neutrons would decay into protons, and you'd have no neutrons in the universe, and so like it wouldn't be possible to form structure. Um,
Wait,
because
what?
of the fact that
Mhm.
sorry.
Oh no, go ahead. I
Well,
wanted to ask
I,
you
I I
about
think
that.
I think you have it backwards. Sorry, like neutrons are heavier than protons just by a bit. But you're saying if it goes the other way around,
Oh yeah. Protons are heavier than neutrons, and protons would decay into neutrons, and then
yeah,
Okay.
yeah. Well, I guess that there are many things that would go wrong, right? Like the fact that protons are stable, it's just this. Okay, so there are two facts, right? First of all, proton needs to be stable. If protons are not stable, like there'll be none of us. Like there'll be no life, basically. You can't make atoms, right? And the second fact is that we want neutrons to decay to protons because protons are kind of more helpful than neutrons a little bit because neutrons are just neutral, right? It doesn't create more complex chemistry and whatnot. Like you said, like the chemical properties of hydrogen right, is determined by the proton, not by the neutron, right? You get all these,
Mhm.
you get all these isotopes in chemistry, right?
Mhm.
Now there's a third fact um, that, and it has to do with the nuclear decay, and that has to do with the stability of different nuclei, right? We know in school that a hydrogen is just one proton, and maybe occasionally a proton and a neutron could bond together, and that's like heavy water, right? Or sometimes you have tritium. You can have one proton and two neutrons, but nothing more. Like if you have too many, it becomes unstable. Without a weak force, then you can get any combinations for hydrogen. You can have one proton, you can have 5 neutrons, you have one proton, 20 neutrons, or 30 neutrons, right? Now you imagine you got a cup of water, right? You know most of that water is H2O. Most of that hydrogen is just a proton. So take a gulp of that water, and the chemical reactions it's anticipated, right? It's us
Mhm.
anticipated. But now all of a sudden, like if your water the if your water nuclei is all over the place, sometimes one neutron, sometimes two, sometimes three, four, five, six, seven, eight, nine, 10, that'll be a whole mess. I think the chemical properties will differ dramatically, right? We know that isotope somewhat affects chemistry, typically not. Is because the isotopes don't differ that dramatically. But without the weak force to kind of weed out these weird guys, things could be quite different. But that's just one of many effects.
Okay,
So
so
just to
are you saying,
summarize,
wait, can I just clarify what that says?
yeah,
Tim,
go
are
for
you
it, go for
saying
it.
what would the universe look like if the up and down quarks were exactly the same mass? Is that what you're getting at?
Yeah, I think so. Like hypothetically, imagine if we were to just get rid of the weak force forcefully, just like we don't like you in our universe. What would happen, right?
Uh-huh.
Yeah. So just to summarize, Tim, what you're saying is if there was no weak force, if I wanted to, let's say, drink water, every like water molecule would have a variable number of neutrons in them. And so it would be like a very like weird water. It would be like a weird kind of like heavy water on steroids in some sense. A
Yeah,
variable stochastic heavy water kind of a thing.
yeah. I don't know. The atoms would be kind of chunky, I guess, some of them.
No, it's way
And
crazier than that, right? If there was no weak force, if there was only a strong force and a U1, then it would everything would look different, right? Then the
well, of course,
scale
yeah.
strong force, the scale of the strong force would set the masses of every particle, right?
Well, yeah, but of course, yeah, there will probably be even more dramatic changes than what I'm describing. But let me just say that this is like an impossibility. Like the math just is not even consistent. But if we
No, it's
kind of
consistent. It just leads to something that's completely almost structureless. Right?
right, but I'm saying if we try to keep everything else the same, but kind of just evict the weak decay, right?
Yeah.
That's you know
Mhm.
then the nuclei will get kind of wacko. Basically, you have like uncontrolled fusion, basically.
Hmm. When you say uncontrolled fusion, that means like a bunch of neutrons coming into the nucleus and fusing together. Is that what you mean?
Yeah, basically, like whenever you toss a neutron to something, it will just stick to it. That's it. There's
So yeah,
nothing
that's
stopping
very
it.
great.
Oh.
No, if there was no weak force, right, then when the strong force combined, it would just be a bunch of color neutral states not interacting with each other, flying around the universe, right?
No, there will still be some residual attraction between nucleons.
Yeah, but
Wait,
maybe like
we
short distance, but not from far away for sure.
Right, not from far
Everything
away.
would be confined away. Yeah.
Right. Yeah, but like for example, if I bring my hands together, let's say okay, well there is still electromagnetism repulsion, but imagine I have like a block of neutrons here, which they will be stable, and
Mhm.
then I just move my hand to that block of neutron. Well, lo and behold, there's fusion happening. The
Wait, would there
neutron.
even be neutrons if there was no weak force?
Ah,
If there was no weak force and we just had a strong force and electromagnetism, then at large distances, then
There should be
it would be,
neutrons. These neutrons would be very chunky.
oh, everything would be a neutron.
Or
No,
what?
they,
I mean, everything would be a
they could be
neutron.
protons and neutrons.
Um,
Some will, yeah. I mean,
huh.
this hypothetical scenario actually is inconsistent mathematically.
Wait, why is it
Mm.
consistent mathematically?
Yeah, I
You
don't
can
think
have
you
a
can.
theory with just color and electromagnetism, and then like when you zoom out to a certain extent, everything like is paired up in something like a proton or a neutron. Yeah.
So can we take a step back and summarize what you just said to the audience? I heard terms like color neutral, neutrons fusing into my hand. Like, what are we trying to say ultimately if the weak force didn't exist? How would you kind of sum that up? I'm gonna point this to Tim because Tim is looking very smug over
Yeah,
there.
yeah. I would say that one of the reasons why um, the up quark is different from down quark, and ultimately why the neutron is different from the proton, is due to the weak force, right? I
Hmm.
mean, of course, we can still say, well, we also know that the neutron does not have charge, the proton has charge, right? Um, but let's ignore that fact for now, okay?
Hmm.
We'll come back to that. But without the weak force, then in some sense, the proton and the neutron will be kind of on the same footing. Uh, and then there will be no way for them to convert to one another, basically, right?
Hmm. Wait,
And all,
you mean one way though, right? Because protons don't decay, but neutrons do decay.
right, but without the weak force, they wouldn't, basically.
So
Yeah,
there'd be
without
no way for neutrons to decay into protons without the weak force.
exactly. And then in some
Yeah.
sense, there also will be no almost like no regularization, like no how to put it. There'll be no police in the universe to say, hey, how many protons and neutrons are allowed in the nuclei, right? And
Huh.
when that happens, it's kind of like nuclear anarchy, basically. You can just have
Hmm.
all kinds of combinations of um, maybe not all kinds, but um, but neutrons. You can just stick neutrons in random places, and they will just stick
Hmm.
to their nuclei, right? In some sense, neutrons will become kind of a well, neutrons are already kind of dangerous particle in some ways, um, but but we don't see neutrons floating around in the universe because they decay,
Hmm.
right?
Hmm.
So they better be trapped in something else. But without that, without the weak force to kind of weed them out a little bit, you could
Hmm.
just see like chunks of neutrons floating around in the universe. They're just stuck together, and then occasionally they can bombard you with into your hand and just start a nuclear reaction here and there and there and there. That's just
Hmm.
one of the crazy things that could potentially happen. But I'm sure that I know Mikey is looking at me like many things will go wrong probably before that even happens.
I'm just trying to
So
think. I can't think. Yeah.
yeah,
I know that's not the craziest one.
that's probably yeah. So what I described probably I'm not even sure if it's mathematically consistent because you can't just be like we move one thing and everything else kept the same because when you remove one thing, many layers of different things change. But we're running some thought experiment here.
Yeah. 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 Very counterfactual. Like if you didn't have the weak
Right,
force,
right.
what would happen? So I guess kind of taking a step back, like going back to the title of this episode, why did we call this the spiciest force? What's so spicy about this? Like besides the term flavor, is there anything like how you would describe it, like where this makes the universe interesting enough, or something along those lines?
Yeah, wait, is it fair to say, okay, so we were talking a lot about this flavor analogy, but like in a literal way, we talk about like up fork, down fork, bottom spring, whatever. If it wasn't for the weak force, these would all be the same particle. There would be no distinction between any of the flavors. The universe would be completely bland without the weak force.
Hmm.
You just have one, essentially one type of fork, um, and that's it. And what can you build with just one object? Yeah, it's
Yeah, I guess it's more than that, right? Like the different flavors will be kind of like colors in a proton. Like
and then not real.
right, exactly. Like you can't really tell if a quark in a proton is red, green, or blue. Basically, you can't tell because it
You
doesn't
wouldn't
make
be able
any
to build
difference.
any kind of particle without the weak force.
Right. And it would be a shame if in our universe up, down, up and down quarks are the same, right? Then in some sense, there wouldn't be things interesting that happens. And also, this is a little complicated, but when we talk about the weak force, we're talking about like the whole paradigm of the weak force, because the weak force actually isn't just one force, right? How the like the
Taxonomy of forces, that's a tricky one.
Yeah, it's a bit of like usually when physicists talk about the weak force, we like to talk about the weak sector, basically. It's kind of like a whole shebang of mathematical machinery plus
It's completely ambiguous how many forces there are. It depends on what you mean by
yeah.
force.
Yeah, so generally the weak sector, to talk about it more colloquially, um, involves not just the forces component, it also involves the Higgs field. So the Higgs field, the Higgs particle is a subset of this weak force sector, and also in some sense, electromagnetism is also a subset of it because um, we know in physics that electromagnetism and the weak force are one of the same thing. It's unified under the name electroweak. So you cannot talk about one without the other. So really, the weak force is a one big family and one big portion of our model of particle physics that gives particles the kind of the flavor, I guess, the characteristic that exists, like Mikey was saying, up, down, or the electrons versus the neutrinos, like all this, it gives it that different flavor in the different particles. And I think that's why it's kind of like a spice that adds to our model of particle physics.
Yeah, that makes sense. That makes sense. I guess like so what you're saying is that like the weak force as you described is actually much larger than just like particles changing to other particles. It incorporates the Higgs mechanism, which is this whole Higgs boson thing that they tried to discover at LHC and eventually found evidence for that, or statistically significant evidence for that, and then also electromagnetism. Is that correct?
Yeah, and I want to add, so of course the Higgs boson everyone is familiar with, but in the electroweak sector we also have these guys called the W and the Z boson. They are should I say they're somewhat similar to the Higgs? No, not exactly, right? These are the type of particles that help create these changes in the flavor of some of these particles, right? And also help drive decay potentially, and also different kinds of interactions. So
Would you describe them like, maybe this is like too loose a term, like if a photon had mass and there were three of them?
that is somewhat fair. Like
Okay.
if the photon is trying to basically, if a photon, the particle of light, is trying to mimic the gluon in some ways, okay, then what it would have is it would have friends, just like how gluons have different colorful friends, right? Then the photon will have different friends called the W and the Z bosons. And because of the Higgs boson, um, because the Higgs field, really, these particles will also get mass, right? And that mass, combined with the properties of the electroweak physics, allows them to create allows them to kind of channel radioactive decay and whatnot. But but hopefully we've emphasized enough that the radioactive radioactive decay is just one small aspect of this whole machinery of the electroweak physics.
And then, as a final question, why is it called the weak force? Like, seems like a very like I don't know, very kind of put down kind of title for a force that's that
Yeah.
significant. Yeah, I guess
I
like
think we don't really like. I think that's. I mean, it's definitely a misnomer. Like at the time, it was just observed that like you don't see its effects that much. So in a sense,
mhm,
it's weak in that sense. You could say the same thing about the strong force. We don't see its effect in everyday life, but because of what we discussed in the previous episode, the nature of it, the fact that it gets stronger with distance, you just can't call it the weak force. So it's like, yeah, it's it's a weird
Yeah,
kind of etymology.
yeah. I think it's like people thought it was a force that's really weak because they only look at one particular aspect of that force, right? Of course, when you look at decay tends to be rare processes, and because of its rarity, people thought of it as, oh, it's seems like a relatively weak force. But I want to add that it's weak because of kind of the world that we live in right now. We usually don't have a lot of energy
mhm,
because in order to change the flavor of certain particles, sometimes you have to inject enough energy for it to overcome the difference of the mass, because mass equals mc squared, right?
mhm,
So because of that, um, and also, well, there's other technicality. You have to overcome more barriers to access this, flavor changing potential. Basically,
mhm,
you want to change the flavor of some of these particles. You got to put in the work to do the cooking. So,
mm,
and because back in the days, people didn't really find a way to access these, um,
mhm.
so it's people perceive it as kind of like a weak force. But really, I think it's circumstantial weak force, I would say.
Mhm. Makes sense. Makes sense. So we're almost at time. I want to leave you guys with a few minutes to leave any closing thoughts you have to the audience, either Tim or Mikey.
Yeah, I mean, so we've been talking about the weak force in kind of this way, like what kind of role does it play in the universe? I feel like we didn't have enough time to get to discussion about why it's that way. And that's an interesting discussion, which I guess we might have later. Um, but it's true, like the weak force is weak because we don't really observe its effects very often. As Tim said, it's only associated with very rare events. The reason
Mhm,
why that's true is because it was hidden away. This force used to be a very prominent member of the universe, and then something had happened that tucked it away and basically suppressed its effects. Um, and it's kind of similar to what happens with the strong force. Like, when you look very, very small distances, you can see the strong force effects very, like, quarks popping in and out. But when you zoom out, you see that these effects are very, very suppressed. So it doesn't affect our everyday life. Like, why is that the case? That there are these forces
mhm.
that somehow don't affect our everyday lives, but matter for things that are very disconnected from our everyday experience. That's a whole different question. And yeah, I'll get to talk about that soon.
Yeah, but
Mhm.
but I mean, just because something is apparently weak does not mean that it doesn't deserve our attention. To study in greater detail. And of course, because of its apparent weakness, that's why it took physicists a long time to kind of really discover and uncover and understand what its importances are, right? And ultimately, um, and if you come back to humanities, like the weak force, one of its effect is radioactive decay, and unfortunately, that led to things like I don't know, atomic weapons and also nuclear energy. Some positive and some not so positive facts about our life. But ultimately, all that is possible is because we finally understand forces like these, right? Um, and of course, let me go back to the beginning point. Like we cover quite a few forces now: the strong force, the weak force, I guess, and gravity. And a lot of people say, there are four fundamental forces in the universe, right? Like, it's very plausible that there could be other forces that are maybe even weaker than the weak force apparently right now. That's why we haven't seen it. But it could perhaps play an even more important role than some of the forces that we know in scoping our universe. So I think the weak force is a lesson to tell us that we should always keep our eyes open, because there could just be more forces waiting for us to discover, and perhaps even more important. So I guess we shouldn't judge a force by its strength. And it turns out to be quite spicy one at that, the weak force.
Reminds me of the phrase like big things come in small packages. Yeah. Well, on that note, I want to thank everybody for joining us and see you all next week.
Yeah, see you all next week.
Yep.
Bye.